Extraction of iron from its oxides. Let us analyze thermodynamically which reducing agent will be more suitable to reduce iron oxide to metallic iron. From the Elinken's diagram we can understand below 1000 Kelvin, carbon that is getting oxidized to carbon monoxide line lies above the iron getting oxidized to iron oxide. Therefore, we can understand carbon monoxide formed is less stable than the iron oxide formed below 1000 Kelvin. Therefore, carbon cannot act as a reducing agent to reduce iron oxide to iron. Then what will be the suitable reducing agent to reduce iron oxide to iron below 1000 Kelvin? That will be carbon monoxide. You can see in the Elingen's diagram, carbon monoxide that is getting oxidized to carbon dioxide line lies below the iron getting oxidized to iron oxide. So carbon monoxide will be a suitable reducing agent to reduce iron oxide to iron below 1000 Kelvin. The next question is what will be the suitable reducing agent to reduce iron oxide to iron above 1000 Kelvin, that is around 1400 Kelvin. Around 1400 Kelvin, the suitable reducing agent will be the carbon that is getting oxidized to carbon monoxide. The Ellingen's diagram you can very well see carbon that is getting oxidized to carbon monoxide line lies very below to the iron that is getting oxidized to iron oxide line. So when we couple these two reactions, delta G of the coupled reaction will have large negative value. So carbon will be the suitable reducing agent to reduce iron oxide to iron above 1000 Kelvin. This can be confirmed using free energy calculation, which is shown on the top of the graph. In the Ellingen's diagram you can see around 1400 degrees Celsius delta G of formation of iron oxide is equal to minus 341 kilojoules per mole. Let's consider the reverse reaction, that is iron oxide getting reduced to iron. So delta G for that reaction magnitude will be the same, whereas I will reverse this sign. So delta G for that reaction will be equal to plus 341 kilojoules per mole. Consider the next reaction, carbon that is getting oxidized to carbon monoxide. Around 1400 degrees Celsius, delta G for that reaction is equal to minus 447 kilojoules per mole. So when you are going to couple these two reactions, you will just sum up the magnitude, sum up the values of delta G for those two reactions. So delta G for those two reactions is found to be minus 106 kilojoules per mole. For 2 moles of iron oxide, this is the value. So for 1 mole of iron oxide, you will just divide the value by 2. So delta G for the reaction will be equal to minus 53 kilojoules per mole. Since delta G is having a negative value, it confirms that the reaction is feasible. We are going to extract iron from its ore, namely hematite. The chemical formula of hematite is Fe2O3. The first step involved in the extraction process is the concentration of hematite ore. To concentrate hematite ore, the powdered ore is washed with stream of water. When we wash, the lighter earthly impurities will get washed away along with the water and the heavier ore will settle down. The concentrated ore is then subjected to a process, namely calcination. The ore is heated strongly in a limited supply of oxygen in a reverberatory furnace. On calcination, moisture content in the concentrated ore can be removed, as well as impurities such as carbon and sulfur are converted to their volatile oxides, that is carbon dioxide and sulfur dioxides, where those two gases will escape. In addition, ferrous oxide present in the ore will get oxidized to ferric oxide. Now let's see how iron is extracted from its roasted ore. The process of extraction of iron from its ore is known as smelting. The roasted ore is mixed with coke and limestone. What is the role of coke and limestone here? Here, limestone acts as a flux. That is, it can combine with the gangue present in the ore and it will form a molten slag which can be easily removed. Then what's the role of coke? Coke can act as a fuel as well as it can act as a reducing agent by converting itself to carbon monoxide. The roasted ore, coke and limestone is called charge. This charge is added to the blast furnace and simultaneously hot air is blown from the bottom of the blast furnace. So what happens is that this coke, that is carbon, will get burned to produce carbon dioxide. As a result of this combustion reaction, lot of heat energy will be produced and the temperature at the bottom of the furnace will rise up to 2000 degrees Celsius. This region is called zone of combustion as combustion of coke takes place here. Now let's see what happens in the middle region, that is zone of fusion. The carbon dioxide produced in the lower region will rise up and in this region it will react with unburnt coke to produce carbon monoxide. The carbon monoxide produced in this region will reduce the iron oxide to molten iron. This molten iron flows down to the bottom of the furnace and limestone will decompose to produce calcium oxide and carbon dioxide. This calcium oxide will further react with silicate impurities present in the ore to form calcium silicate or slag. This slag will be formed in the molten state and it flows down and floats on the molten iron. If you consider the reactions, reduction of carbon dioxide to carbon monoxide as well as decomposition of calcium carbonate to calcium oxide, both the reactions are endothermic in nature. Hence, the temperature of this zone will reduce to around 1000 degrees Celsius. So, the temperature at this region will be around 900 to 1500 Kelvin. In this region, slag is produced in the molten form. Hence, this region is called zone of fusion. The carbon monoxide produced in the middle region will rise up to the upper part of the furnace. In the upper part, carbon monoxide will react with the roasted ore that is coming up from the top and it will reduce that Fe2O3 to spongy solid iron. This solid iron will move to the lower region of the furnace where the temperature is higher, so it melts and it becomes molten iron. This region is called zone of reduction since reduction of iron oxide takes place. The examination point, all the balanced chemical equations has to be memorized because they may ask you to write the chemical reactions involved in the extraction of iron at 500 to 800 Kelvin. Now let's see what is pig iron. The iron obtained from blast furnace contains about 4% carbon impurities and many other impurities such as sulfur, phosphorus, silicon and manganese in small amount. This is known as pig iron. Let's summarize the extraction of iron from its oxide ore, that is hematite. In a blast furnace, we will take roasted iron ore, coke and limestone and simultaneously we will blow hot air from its bottom. As a result, coke will be burned to produce carbon dioxide and it gives out large amount of heat energy. As a result, temperature in the lower region of furnace will rise up to 2000 degrees Celsius. The carbon dioxide produced in the lower region will rise up to the middle region and there it will reduce the unburnt coke to produce carbon monoxide. This carbon monoxide produced in the middle region will rise up to the upper region and there it reduces the iron oxide to spongy solid iron. The spongy solid iron will move down to the lower region of furnace where you have very high temperature. Therefore, it melts and you will have as pig iron formed at the bottom of the furnace. In the middle region, calcium carbonate will decompose to produce calcium oxide, and this calcium oxide will react with the silica impurities present in the ore to produce molten slag. This slag will flow down and it flows on the molten iron, and it can be removed separately. When we heat pig iron along with iron scrap and coke using hot air blast, we get cast iron. This cast iron has around 3% carbon impurities and is extremely hard and brittle. The purest form of iron is called wrought iron or malleable iron. This is prepared when cast iron is heated in a reverberatory furnace lined with hematite. This hematite oxidizes carbon to carbon monoxide and reduces the carbon content present in the iron.